Good morning, neighbors. I'm going to link to a video below that you might consider tedious or why or what, but it's just very well done. It leads into more. It is not a whole bunch of answers for you, sorry. It is part of the rest of the story, I suppose. Anyway, quantums, that word. The word in science has distinct meanings depending on the audience. Go figure. You've seen quantum. The word used is speculation, is fiction, is nonsense, is crystal healing. These quantum energies. But in the sciences, using calculus usually, you begin to learn how the quantums are defined, what the boundaries of the quantums are. Quantums used in the measurement sciences. Optical emissions are called quantum measurements. These are often measurements that are related to subatomic properties. In other words, the size of the core of an atom, whether it's an element or an isotope of that element, makes distinct and unique changes to electron orbitals. And that's kind of what a lot of what we're talking about is electron orbitals, which are measured in quantums. We're getting good enough to see an electron, an individual electron. It's still measured in quantums, oddly. Very defined quantums using calculus. And then you add a very detailed calculus called differential equations into that. And that thing called differential equations are what the name implies, difference equations. These equations are based on a time, or these equations are based on a chemical reaction, or these equations are based on a nuclear reaction. Or these equations could be on the soap you use in your sink. But who goes there? Well, some people do, because the soap you use matters. Someone out there has looked at soap and still looks at soap and wonders about soap. So as long as it can wash wildlife off, I guess it's good. So this quantum measurement idea really needs to be understood. When people pose it in unstructured means, it becomes meaningless, it becomes woo. But when a physicist talks about quantum, when an electrical engineer talks about quantums, he probably won't. He's going to talk about the measurement device. And the measurement device is measuring in quantums. Very odd. It's a strange world, very complicated world. But this idea of quantums, this is big. And I go and I look in Wikipedia. Side note, I opened up my browser and I have a tab for the national laboratories, a tab to A to Z index of U.S. government facilities, a tab open for fuel fabrication, NRC tab, another tab for strange animals and nuclear stories. And then now I'm at how is a quantum defined? And you don't get a good answer for that because the definition is done 9 out of 10 times using some advanced calculus. The role of calculus is to help us learn. It's a tool. So that was my big thing for the day. But the link to the presenter below is good. Well done. And I'm interested in the next video she's going to be doing on the topic, which she mentions towards the end. So not happy with any definitions of a quantum. You do have to put qualifiers on that word quantum. Say you put photon quantums, optical quantums versus electrical quantums. We used capacitors to build sums, summing capacitor. That's where they were put into to measure electrons, basically coming from photons. The measurement scientists, our sciences are very interesting. So, second topic here. Yeah, we're going to try and do two, but we're already at our 6-minute targets here. So, satellite measurements. Another instance of quantums and knowing definitions of how quantums work and what they are and mean, because the satellites are emitting a radio frequency. The satellite knows the attributes of that very specific frequency or range of frequencies. And it just so happens that those frequencies interact with molecules. Molecules in different layers of the atmosphere. This isn't woo, this is how satellite telemetry works in many cases. It's broadcasting a very strong signal, very directed at the Earth, and then seeing what comes back and what doesn't come back. Looking at minuscule changes in femtovolts on detectors for minor differences from a satellite sending a beam down. It can know the altitude of the layers it's trying to get feedback from with massive signal interrogation techniques. Yes, you can interrogate the shit out of signals, but that's part secret, eh? So, these satellites work. We've launched more of these satellites specifically for methane measurements across the planet, but we already know these satellites are seeing leaking gas wells. This isn't my story. Leaking gas wells in the prairies of the Midwest, leaking methane mostly, and other things like SO2 and the other gases that the Earth contains and burps out once in a while that we measure. So this satellite, this one satellite, actually it was two initially I believe, saw these wells, and we've only put up better satellites since then. So now you ask, well, how do we know those satellites are true? We have what are called calibration stations now across the globe. I'm saying we, that is the mouse in my pocket, the existential us, have positioned calibration stations across the globe that these satellites traverse across. And when the satellite comes within a calibration, might be a hectare of land being monitored from ground stations, it starts to use differential equations and applies corrections to its signals based upon ground telemetry. And on top of that, just to make sure of what we're doing, we might send up weather balloons with advanced telemetry and measurement devices that will be in the path of that satellite. And that, more precise measurements because of altitude and better known physics, will be used to calibrate or certify the data from that satellite. The way science works, all of that satellite's initial data is saved. That is the baseline. And then people turn tools loose against supercomputer tools. Things that are doing, I love the word fast Fourier, it sounds so cool. Fast Fourier transformations, more math, applied math. So these satellites get calibrated multiple different ways. Why would I know about this? I was trained on these things, the calibration of things, the calibration of most things. It was an interesting set of classes. So that's how it works. And I tracked the industry. There are projects out there about these ground calibration stations for satellites. One of them, it's still out there, but it's buried. Earth Observing Network, EON, was the original name for this. You can go look at their employees. They might have jobs out there that go out and certify those hectares of instrumentation or those acres of instrumentation to make sure they're working properly and doing their job, because they're ground stations that are sensing the same things those satellites are, only the ground station is on 24 hours a day, where the satellite might traverse only once every 3 days across that ground station's location. But mind you, we have dozens of these, maybe more, because other nations are doing this. This is a global exercise in understanding planetary climate. How do you close the planet? A wall won't work, but math will. You can bound the rules of your math for the planet. You can set where the atmosphere theoretically stops and use bounded math called calculus. It's a big world, but those satellites work. The challenge is we aren't seeing the data well presented to us. We're hearing bits and pieces of it. You don't see people talking too much about that satellite data. I've seen some people dismiss the satellite data. They've been up there a long time doing a lot of things. The military satellite is even a more impressive array of detectors and physics. Now we can see pictures of a dollar bill on Earth from space, but our military could do that long ago with constraints. So, how'd I go? 12 minutes. Peace is out, neighbors. I hope 2022 is another year.